Hello, this is chapter 6. I'm going to break this into 2 videos. It's actually 2 different class periods, but I have them all in one document, so it's easier for everyone to deal with. So this is going to be chapter 6, and this is going to be video 1, and you'll see where we do video 2 in a minute. Now I made sure that all these links had all these pages have nice live links. You can see right here, if you want to go and read about what we're talking about in OpenStax, you can go right to the section. I also made it so that, the different links that are in this, they're all live links. I've got some links that are examples of something you might see in the lab, so try to make it relevant to you so that you can see what's going on. Now this first section of OpenStax should be a reminder of chapter 2 to you. So a lot of it should seem really familiar, so it should seem a lot like chapter 2. It shouldn't seem like it's new material, because it isn't. Just as a quick reminder, we've said this several times, but on your periodic chart, when we're looking at it, if we're trying to tell the difference between something that's ionic and something that's covalent, we've talked about how the 1, 2, 3, 4, 5, 6, how you've got your stair steps right there. And if you're doing something that's ionic, then it's going to be something that's on this side. So we partly have that side and something with something on this side. That's our look of our something that's ionic. Whereas with covalent, both things are on that same side. And the only reason why this is mattering in this chapter is because they use this word formula mass. And in chapter 2, we talked about the word molecular mass. They mean the same thing. It means you go to the periodic chart and you grab the number that's on the periodic chart and you bring it over and you use it as moles per gram. And if you have a lot of things on the periodic chart all in the same compound, then you add them up and then you have the mass of the whole thing. So we have some examples. There are 4 species below. You're going to circle the compounds. So compound, that would be something ionic. That are made up of formula units. So that's just that word. Remember we talked about before, we use the word formula units to talk about one little unit of a compound. And if you have a formula unit, guess what? The mass you get off the periodic chart is just called a formula mass. So if you see formula mass, don't let that throw you. It just means get the numbers off the chart, add them together. So if we look at these numbers right here, we have sodium chloride, and sodium's here, and chlorine's over here. So definitely that one is ionic. We look at magnesium chloride, he's here, and again the chloride. So ionic. And then we've got something, this is on the left side, over here. And then this is a group, it's a polyatomic ion, it has a charge. So because this has a charge and then this sodium has a charge, we know that sodium is +1 and that there's 3 of them. We know that. Then we also know that this guy's ionic. Now when we look at this last compound, we're going to put a square around it because the carbon and the oxygen, they're both over here on the right hand side. And then remember, hydrogen is one of the only things that bonds in all different kinds of ways. And it's a nonmetal, and so we're going to be calling this bonding. When it's with things like carbon and oxygen, we'll be calling it a covalent bond or a molecule. So this is a molecule, whereas the other ones are compounds. This one is our only molecule, made up of molecules, and so we would call the numbers we get off the chart the molecular mass, but notice in all those cases, you do it all the same way. Keep in mind that when you have a 2, don't forget to multiply by 2 before you add. You got a 3, don't forget to add by 3. The 4 only applies to the oxygen. It does not apply, make sure that looks like that's going straight to oxygen. It does not apply to the phosphorus. And then our hydrogen over here, he's got 2. And you just add it all up. Now keep these numbers in mind because we're going to use them later on in the next section. This just reminds you how to calculate formula, molecular mass. You've seen all this. There won't even be Newton on it. It's just everything kind of builds on remembering that idea, and you haven't seen it in 2 chapters, so just remember it. It was important, still is. Now this section has 2 Dr. Bean videos. Again, they're live links. go ahead and check them out. She says things more
Because
quickly
of the law
than I
of
do.
constant composition,
So, and more
we know that
she can
that
say
is
something
carbon.
in a lot
Because
less
of the
time.
law of constant composition, we know that that is
You guys
carbon.
see? All right, so all those links, those work. They're like, I don't know, they're under 10 minutes. Each of those links are under 10 minutes. And if this explanation doesn't do it for you, and if what Dr. Bean is saying, if that doesn't work for you, Tyler DeWitt is great at explaining things in really, really like clear language with all the steps shown. And there's 2 different sets of videos for him. And then Melissa Marable is someone I discovered last year, and she's real current. The way she describes things, she uses a lot of pictures that are digital pictures, and I think that she does a very good job explaining things also. Okay, so scientific data. It's often used using percentage values. Now, this is true for percent composition, which is what we're about to talk about. And this is just a reminder, this is not new to you, because y'all know I like to say non-political things, right? So non-political percentage calculations. You guys use these in real life. So usually at this point I would stop and I would say, what's a percentage you use in real life? Okay, so interestingly enough, one that pops up a whole lot is body mass index. Another one with the sports fans could be batting average. You can think of other things. I always throw out there that our grades are a percentage calculation. I just want to point out, percentages, you use them in real life. They give useful information to you, and they also give useful information to scientists. So that's why we use different kinds of percentages. This first type is percent composition. So we're basically going to be doing 3 different kinds of calculations. This is the first type, percent composition. And just a reminder, a percent, it's just the amount of something over all of it. I'm going to say part over the whole. I just want to let you know too, percent composition is like a subcategory of this word percent mass. So in Newton, if you see percent mass and you're trying to think of that, it's the same thing as percent composition. Yes, if the problem looks like the kind of problem we're working on, then yes, it's the same thing. Percent mass is like a bigger category, but different books use some different terminology. OpenStax uses percent composition. If you see Newton using percent mass, like send me a picture email and I'll message them. They've already fixed a few things they say they fixed a few things that I've asked about. All right, so percent composition, this is like any other percent. Remember, part over a whole. So this is just one type of element over the whole thing. Notice this is in grams and grams. Don't forget your times 100%. Don't forget to do that. So what is this saying? What does this mean? How on earth are you going to use it? It seems like kind of a weird formula. Okay, so it's actually really easy. So check out this problem and this will kind of explain it. So determine the percent composition of carbon in C6H12O6. What that means is that we want to know the total mass of carbon over the total mass of the molecule. And I know it's a molecule because it's just got the carbons, hydrogens, and oxygens in it. It's low key. In chemistry, we do things like, hey, assume 1 mole. Hey, assume 100 grams. You're going to hear both of those, and it's a great thing to use. So we're going to assume 1 mole of the compound, and it's going to help us cancel out one of our units if we do that. So following Dr. Shea's suggestion, we're trying to find the percent amount of carbon. So just remember, you're going to take the 6 moles. So see there's 6 of those. Oops, that is too dark. See how there's 6 of those though? Right there, there's 6 of those guys. That's why we use the 6 here. Because we're trying to figure out the total carbon weight. And then the 12.01 is just a number from the periodic chart. You look up carbon, that's the number you get. And if you add these guys all together from the periodic chart, make sure you don't forget to multiply 12 for the hydrogen and 6 times oxygen. If you add that all up, you're going to get 180.18. So this is pretty easy. Just put it in your calculator. 6 times 12.01 divided by 180.18 times 100%. You're going to get 39.99. Now, just be aware that the sig figs for these things, and Dr. Bean says it this way, that they can be a little squishy. And what that means is that, well, our percent composition, these are kind of based on how good our instruments are at figuring out the composition. And we need to always make sure that our compositions add up to 100. So sometimes I'll round up to this position, even though it should be this position, to make it equal 100 properly. Here's the thing for you guys. It's not going to be a questionable situation for you. So if you get 39.99, it's going to work. If you get the 40.0, it's going to work. Like on a test, your answers, it's going to work out like that. So in general, keep to the right number sig figs. So keep to them. But if you ever see like an example problem somewhere where someone doesn't quite have the right number of sig figs, don't freak out, because maybe the instrumentation they're using isn't great. Okay, so we've got some examples to practice. Now, in class, what I would do is I would pause and I would say, you've seen the example, now you guys work all these problems. And because I'm trying to make this like a learning and an active experience for you, I really suggest that you go ahead and pause the video right now and try to work these out. And I do have a hint that the formula mass for all of these are on the first pages. And actually the individual masses are also all on that first page. I said they were coming back, and here's where it is. Okay, so pause the video. No, like really, you want to pause the video and try to do these on your own to see if you've got the idea. All right, so I'm going to go back up and I'm grabbing the NaCl's number. It's right here. That 58.44, and I'm going to make sure I've got the other two numbers handy also, the 22.99. So 22.99 divided by 58.44 times 100%. And if I want to go ahead and do the chlorine, I can say 35.45 times 100%. Okay, so what I'm really saying is, since there's only one of these guys here, we don't have them in there, but like they both are one. What I'm really saying is 1 mole of sodium times 29.99 grams per mole. So now see, our moles are canceling of sodium. And then this is the guy where I assumed 1 mole. So this gram per mole, the mole part also cancels, which is great. And then now our gram units are going to cancel, because in both cases we're talking about masses. So a percent number should come up with only a percent unit, right? You don't want to have a gram and a percent unit. You got to only have 1% unit when you're doing it. So got my calculator handy. I'm just going to put in 22.99 divided by 58.44, and I get 39.34%. So that looks good. I'm going to go over here, 35.45 divided by 58.44, and I get 60.66%. You'll notice these do add up to 100, which is great. That's my sodium and that's my chloride. Now you could ask a question right at this point. Okay, I have only got two things in there, so what do they have to add up to? I kind of already mentioned it. They have to add up to 100. So once I got him, if instead of doing the math here, if instead what I wanted to say was 100 minus 39.34, that would have worked also. So you can do it that way. If you had three things, you would have to subtract. You would have to have two of the values, because you'd have to subtract 2 from the 100. You'll see in a minute what I'm talking about. Not this problem, but the one after. All right, so then we're going to do magnesium chloride. So again, I'm going to zoom this back out, and I'm going to go back up to get that magnesium chloride number from the top. Oh, phooey. It won't stay small. There we go. All right. So over here, our bottom number was 95.2. Our top number is 24.3. magnesium. Now, want to be careful not to make the mistake of dropping any of the chlorines. There's 2 of them. So I want to make sure that I'm saying 35.45 times 2. Alright, so I'm going to grab those numbers, put in my calculator. 24.3 divided by 95.2 times 100. That gives me 25.53%. And then over here, so I can either plug these numbers in, but since I've only got these 2 elements in here, I can also say 100 minus 25.53. And that'll give me 74.47, which thankfully does add up to 100. You can kind of glance at those. I'll go ahead and throw the numbers in as a double check. If you were on a test, I would also just double check yourself, because you'd hate to miss something like this, because you can already tell the math isn't very complicated and it relates to concept that you've already done. And I'm getting the same exact number in my calculator. All right, so now we have the Na3PO4. Let's switch back. So I'm going to go back up the Na3PO4 number. It's up here. So Na3PO4 is 163.96. And again, my sodium, my phosphorus, and my oxygen. I'm going to do my sodium over my 163.96. Don't forget that there are 3 of them. My phosphorus, and if you can't remember phosphorus, you can pull it back up. It's 30.97. Do I have more than 1? Nope, there's just 1. And then the last one is the oxygen. Don't forget, that one is 16.00 times 4 over 163.96. All of these are times 100% too. I shorted myself there. All right, and come back up. I'm going to zoom back out. So just grab my calculator. 22.99 times 3 divided by 163.96 times 100. You can do this in any order. I get 42. Whoops. .07% for him. Now at this point, I can't subtract to get phosphorus because I've got 3 elements in here. I gotta have at least 2 before I can do the little subtraction trick. So 30.97 divided by 163.96 times 100. And I get that this one is 18.89%. And then, again, if I'm going to do the subtracting thing on this one, it's going to have to be 100 minus 42.07. Oops. And then also minus 18.89. Or we can just put the numbers in. I don't know which way you want to do it. 16 times 4 divided by 163.96 times 100. And I get 39.03. This is one of those ones where it's a little slightly off. It's not quite adding up. I'm going to see what I get when I do 100 minus 42.07 minus 18.89. And so this one gives me 39.04 because we subtracted it from 100. Here's what I will tell you is that right here, this was originally a 6 and a 5. So if I just, and that 5 is really close, if I just kept it at a 6, then this being a 04 would work. Again, we aren't getting super picky about this. This is Gen Chem. You are not trying to submit some kind of data for a national research paper. This is Gen Chem. If you get 39.03, 39.04, you get something very, very close, then that's totally fine. And do make sure your numbers add up to 100, approximately. So you don't want them to be like way off. So that's that one. So that's the first math technique. Now we're going to just review a few ideas. So we also talked about empirical formula in the other chapter, in chapter 2. When we talked about it, it was the smallest whole number ratio. And I just remembered it. So like if I was in class, what I would do is I would stop, because I'm trying to keep this interactive and I'm trying to keep you engaged in thinking about it. So I'm going to go ahead and pause. And I've used this one, and you go ahead and fill in the other ones. So pause the video, give yourself a chance to think before just getting the answer. Okay, so those ones are empirical formulas. C12 is not an empirical formula. The physical and chemical properties are often very different. Whether the molecule is the empirical or molecular formula can be determined if you are given the mass of one molecule or compound and have calculated the molar mass. This is the same thing as saying molecular mass or formula. It's meaning get that number off the periodic chart. So just to review it, empirical formula is the smallest whole number ratio of elements in a molecule. So those three guys we just talked about, those are the smallest ratios. Like a ratio higher would be like Na2Cl2. They are empirical formulas. C6H12 is not. The empirical formula for that would be CH2. The physical and chemical properties of empirical and molecular formulas are quite different. It's like the difference between saying that something is a gas and something's a liquid. Like they can be hugely different, especially the larger the molecule, the properties become very different. Okay, so whether the molecule or compound is in the empirical or molecular formula, it can be determined if you are given the mass of one molecule and you've calculated the molar mass. So this is a lot of words that actually says something that's really simple. So this is another simple math. You've done this before. I promise you've done this kind of math before. Just not maybe with compounds. So here's our example. What is the molecular formula for this? So this is saying this is the empirical. We have the empirical. What is the molecular formula if the molecular mass is this amount? Now, if you do the C2H5, and I did this one up here. I believe I did this one on the first page. Oh, no, I didn't. Okay, so this one you would do from the periodic chart, and you would just do 2 times the 12.01 plus 5 times 1.01, and you would be getting this mass for this compound. So you take the big one, you put it on top, and then the little one is on bottom. You do the math, and it's going to come out to being like whole numbers. It'll be like a 3 or a 2 or a 1. The 3 means that's what you are multiplying all the subscripts by, not just one of them. Make sure you get all of them. So, again, that 2, I'm going to change that color really quick. So the 2 gets multiplied by 3. And then the 5 gets multiplied by 3. So you get it? You just do the big number divided by the little number. Ends up being 3. All the units all cancel out. And then multiply by whatever that turns out to be. All right, so I got some examples for you. What's the molecular formula of this guy? Here's your molar mass. Oh, I left off a grams per mole. I'm sorry. Should say per mole. If the molecular mass is, and we have these options. So you pause the video and you think it through. Again, that's the big number divided by the 30.03. All of these numbers are divided by 30.03, 30.03, and 30.03. Probably can see this without even putting in your calculator. That one's going to be 2. This is going to be 6. This is going to be 10. And this is going to be 1. So, interesting on that last one. We'll have to do comments on that one. So just multiply all those subscripts by 2. So that will give me C2H4O2. Next one, make sure I'm always going up to this. Don't try to like go to that. That won't work. Always got to go to the empirical to get this. So C6H12, that's a 6, O6. And then with the 10, again, you're going up. C10, H20, O10. And then this last one, CH2O. So what this last one is saying is that we actually are talking about that molecule. It is the empirical formula, but we also are talking specifically about that one. So it is that one's molecular formula. So you can be 1. And that just means you multiply all the subscripts by 1, which means you're talking about the same thing as the empirical. That only happens sometimes, but I just wanted to throw it out there. I didn't see any examples of that in Newton, but this definitely comes up in organic chemistry. So if you're going to be taking organic, you're going to be getting this concept coming up again. And then I have just a little thing right here. So we were talking about these percentages and these molecular and empirical, and you're probably like, well, why do I care? Okay, so we have some instrumentation. There's gas chromatograph, gas chromatography, and mass spectroscopy. These are super common instruments in any lab. They've got like tons of them, more than one at like UTC. Like it's super common, and it's used in the industry. So they're going to have these at companies that deal with chemicals. It's in the industry. It's super common. And like in the case of gas chromatography, like you dissolve a sample of something, you want to know what its composition is in water, or not in water, in some kind of solvent, and you just squirt it in the machine and out pops an answer. You have to like analyze it a little, but out pops an answer. And like mass spectroscopy, it kind of works the same way. It just depends on what you want to know. They do tell you more than this. But one thing it can be used is to verify percent composition and see if something is actually pure. All right, so that was our second math, by the way. So super easy. And our third math, this is not hard math. Okay, so don't think that all these steps means that it's hard math. It's not hard math. But you do have to just keep up with what the order of the steps. So we're going to assume we have a 100-gram sample. We're going to write each percentage. I'm sorry, let me start at the beginning. Kind of got ahead of myself there. All right, so we're doing this one. So this is the third type of math. So again, this was the second type. And then this was like the first type. So 3 types of math that we're doing today. I have a little Newton comment. And it does work for more than Newton. You'll see this in the textbook also. So if the problem says grams instead of percent, the examples we're going to do today are percentage. But if it says grams, do everything the same. Just start at step 2. I'm going to repeat that when we get to step 2. Okay, example. Determine the empirical formula. So I think of these problems as like the opposite of the other problem. So the one like if we go back to the first problem, we go up here. So like in these problems, we were figuring out the percent when we already knew the formula. So now what we're going to be doing is we're going to be given the percent and we're going to figure out the formula. So I kind of think of them as backwards. One's going forward and one's like going backwards. All right, so we're going to determine the empirical formula of a compound. And then here's our 2 percentages. So here's the first step. This is a whole little chemistry assume thing. I promise it works. Assume you have 100 grams of sample. So if you have 100 grams, 82.6 grams would be 82.6% would be this number right here, this 82.6 grams. Do you see that? Because it's a 100-gram sample, we're assuming. So it automatically makes our percentage into a gram amount. You can put it in a calculator too if you don't believe me. Do 82.6 divided by 100 to turn, your percent times this 100 number, and you're going to get the 82.6. You're going to do that for everything that's given to you as a percent. So basically we're just saying rewrite the percent unit as a gram. If you didn't like thinking of it the way I was just saying it, just rewrite it as a gram. You got to have a gram to move forward. And also, like I said, some problems will just give you the grams, so you don't have to do this. You're already given that number, and you would be starting at step 2. So step 2. All right, so here's the key thing. These are mole ratios. Those little numbers, you know, that go at the bottom of a formula, they're mole ratios. So we have to convert grams of each element in the sample into moles. Once we do that, we should have the formula. So you're going to divide by the molar mass. Remember, you can call that other masses, but that's the number off the periodic chart. So here we go. We got 12.01. Again, this is from the periodic chart. Same with this one, periodic chart. Hopefully you're starting to accidentally memorize some of these. And when you do that, you get 6.87 and 17.2. But look, we've talked about this tons of times. You can't have a decimal in here because it implies that you have like part of a carbon atom, and you can't have part of a carbon atom. You either have it or you don't. So we can't have those numbers. And this is one case where you can't just round up. It's the rule you cannot just round. It doesn't work. So like our normal rounding rules, this is one category where it won't work out. So we're not allowed to round up or round down. We have to do something to get these into whole number ratios, and this is a little math trick. It converts all the mole amounts of each element. To convert all the mole amounts to each element if it's not the lowest ratio. So notice, what you're going to do is you're going to divide each mole amount by the smallest number of moles. And you'll round up only after this step if it's in the 10th place or in the ones place. So the reason I picked the 6.87 is because when I compare that number to that number, the 6.87 is the smallest. So everyone gets divided by him. Joop, joop. Oh, look, I get a whole amount of a carbon. That's awesome. So I'm most of my way there. So usually this works and you can stop right there. But in this case, and of course I picked an example that doesn't work out right. Most of them will. It's still not okay. Can you see the whole number ratio? Can you guys see it? 1 to 2.5. It's going to be 2 to 5. You might be able to, it might be that simple for you. If not, then here's the words that say it. This final step is only necessary when the 10th place of one of the answers is something that has a number that ends in a 5 or a 3. You can't use normal rounding rules. So if it ends with like a 0.5-ish, you're going to multiply by 2. If it ends in a 0.33, you'll multiply by 3. So I'm going to take this top number. Here's the number I have. And I'm multiplying, because it ended up that I had one number that had a 0.5. I'm trying to get rid of that 0.5 is what I'm trying to get rid of. So I'm multiplying everything by 2. So the 1 mole of carbon becomes 2 moles of carbon. And the 2.5 moles of hydrogen becomes 5. Like I said a minute ago, you probably already could have seen that just by looking at it, that ratio, 1 to 2.5, is the same thing as carbon to hydrogen 5. And if you like a visual, so if you don't like all the words, there's a nice little visual right in here. It's got the pictures. You got your mass, you divide by the molar mass, by the lowest numbers, convert to the whole number ratio. If this works better for you, then you can use it. I just want to make sure you had that resource. And I'm going to do one last little practice problem right here. So we've got manganese, we've got carbon, and we've got oxygen. Calculate the empirical formula. So if we follow the steps, and this is one case too where I would suggest making sure that you have all of the numbers already, like I would go ahead and do each step all at once. I wouldn't do it once for the magnesium and then once for everything else. And it thinks I'm trying to change pages. I didn't mean to try to change pages. Let me tell it that I'm on page 6 and we'll see. Oh, it does not like that. Okay. So first step, turn them into grams. Now at this point, if you haven't paused the video, pause the video and go ahead and practice the other steps. It is so much better for you to try to do this on your own and have your brain actively engaged than just to watch me do it. So let's say you don't have a periodic chart handy and you're not sure what to do. I do have a periodic chart listed under test 1 and test 2, test preparation. So you can go ahead and get that number from there. It's going to be, this is one that I don't use very often, so I had to look it up. 54 point, wait, let me do this in a different way so it's more clear. I'm going to grab these guys, I'm going to scooch them over. All right. So I'm going to go from grams of Mn to moles of Mn. And so he is 54.89394 grams in 1 mole. That's a magnesium or manganese. And again, I'm doing this all at once. While I'm in the flow of it. This one's 12.01. That's from the periodic chart, and that's in 1 mole. Those are all carbons. I'm going to scooch him over so he's got a little bit more space. And then grams of oxygen, moles of oxygen. This is 16.00 in 1 mole. So when you do the math and get your calculator handy, you're going to say 38.4 divided by 54.94. So I get this one is 0.699. It's kind of good to put a few extra decimal places in this. I could take it out to 4, even 4 places out. That'd be great. I'm going to do the next one, 16.8 divided by 12.01. This one gives me 1.3. Sorry, it's 1.399. So, just letting you know, like I've got that one rounds a lot. And then my last one, 44.77 divided by 16. So this one gives me 2.798. 2.798. So that's my moles of oxygen. This is moles of carbon. And then this is my moles of manganese. So if you can't remember what to do now, if we try to do the formula, you can always try to do the formula at any point, and then it'll tell you if you're good to go or not. So if we try to do that, you can see right away that we've got all kinds of craziness going on because I've got tons of decimals. So I'm going to divide by the smallest one. So I'm going to compare 0.69 to 1.3 to 2.7. Definitely the 0.69 is the smallest one. So when I do that math, I'm going to get one of these. Actually, I've already got the other number in my calculator. So the third number, so I'm going to do that one next. And this gives me 4.000, so that's, or 4.003, so that one's a really solid 4. And then 1.399 divided by 0.699, and I get 2.001. So that's definitely a solid 2. So the way I would write that guy is I would do Mn. Here, I probably should do it on the earlier page. I would call this Mn, because there's one of those. C, there's 2 of those, and O, there's 4 of those. And you can always double check looking at it and say, oh, is that right? Well, this is oxalate, that's -2, that must be +2. You don't have to know that information, but you say, hey, that really is a real compound, so that'll work. And just double check it's the lowest ratio, and you're good to go. So if you can do this problem, you're in an awesome place. Now, I'm going to come back. I'm going to actually make this next one video 3. The idea behind this one is that you were going to work on different sections of this as a class, and I still think that it has definitely has some value in continuing that idea. But chapter 6, video 3, we'll come back and we'll do that one. Last little bit is that in the review, just to check yourself, to determine the percent composition per element, so percent composition was the first math we did, you only need the formula. And that's totally true. You only need something like C4H8 to figure out that you need 4 times the mass of carbon over the full mass times 100%. So yeah, that's all you need. It's just the element. And then the percent composition, it uses the mass of one element regardless of how many are in the formula. So this is true, but if they only ask for carbon, but just note that like it might be a multi-part problem where they ask you for all of them. So they might ask you for hydrogen or something else. So you might have to still figure out all the percentages. But if they just ask you for one element, you only need the mass of that one element. And I'm assuming that you know the molar mass of the formula. Okay, molecules with different molecular formulas, but the same empirical formula have the same properties. That's false. The properties can be very different. And if you know percent composition of each element in the formula, you can determine the molecular formula. So the percentage composition, that again, that's that first math thing. You can go back and look up the first math part. What that one gave was the empirical. Oh, I misspelled it, empirical. Oh, I totally misspelled it. Is that right? Empirical. Yep, so there you go. Hopefully this was helpful and you can go back and look at things. Definitely click on any videos, watch any links that I've got in here if you've got any questions.